So we'll go ahead and get started. So before you want to tune a control loop, we need to ask ourselves first, how do we identify a control loop problem, right? Why do we want to tune this loop? So we need to go down this route of we need to identify our problem maker control loops. So we use a tool called the overview performance chart. And the way this works is we have an engine in the background that's going to score all your control loops every single day, and it's going to represent them as different colors. So my poor performing loops would be red, my okay loops would be yellow, and my excellent loops would be green. If the loop is not in control, it could be in some of these other score states. So it could be in manual mode, it could be saturated, offline. You may just not have historical data for that loop. So this is a way to help us identify loops that may be problematic. There's lots of cool filters we can do here too as well. So I may be interested in troubleshooting an area called 7C. So that's going to be this first block here. I'm going to drill down to that area. And then we could see all of our control loops being these colorful blocks. And it's going to also size them by severity. So the bigger the block, the bigger the problem. So we said red is poor. So I'll pick one of these red big poor blocks. We can drill down further into a performance report to see why it's scoring poor for the day. So we have a flow loop here that is poor due to excess variation in its set point. It has occasional saturation. It's aggressive disturbance rejection and some dominant strong oscillation. So we could see the raw data that was used for analysis, a result breakdown. Anytime we have problems with set point tracking, we automatically flag the loop as poor. And then the metrics that are used to determine that score. So what sticks out to me is, well, this control loop's not on set point. That's its goal. So we monitor a COV, and if we're above that threshold, which the daily index was 3%, our monitoring COV is 1%, we flag that as poor set point tracking. What also stands out is our disturbance rejection. You can see this loop is aggressive. So we expect this loop to settle in a minute. We want this red desired curve. We're actually getting this blue curve. So it looks like this loop is settling possibly in 10 to 20 seconds very aggressively with strong dominant oscillation. So this is a good candidate to a loop that we'd want to tune. And what I would do here is I would slow this loop down. So instead of being aggressive and trying to get to set point in 10 seconds, I want to slow down this tuning and have it settle in a minute so it will follow our desired red curve. So now that I've identified a loop that is problematic, we can pull up that raw data for that loop and do some tuning around it. So I'm going to pull up a sample loop here that we're going to tune. And the first thing you want to do before you tune a loop is you're going to want to do a process step test or a bump test. So what that is you need to put your controller in manual mode and step your output. And as you step that output, you can see the blue output here. We put it in manual mode, so we held the output stable, and then we stepped it down. And as you step down that output, you're going to see your process variable respond. And then we're going to bump it again, step it down. We see that process variable, the green, respond. And then we're going to bump it the other direction as well. So this is a very good example of a step test / bump test. It's important to ensure there's no upstream disturbances. So while you're doing this bump test or steps test, you want to make sure you're not increasing your production. You want to make sure there's no additional flows that could cause disturbances, nothing that's oscillating. Try to hold everything as steady as possible, because the goal is we're going to build a step response between our output and our PV. So if you have disturbances that cause your PV to move around, that would interfere with your step response. And whatever data we have in our trend is going to be used for tuning. So I'm going to ensure that I'm not going to have disturbances in my raw data. So you can see in the PV, there's a large disturbance here. I'm going to remove that by just zooming in on my trend. And this is the data I'm interested in modeling. So I'll zoom into this portion here. And now if I right click my trend, we have a trend extension called Loop Tune. So I'm going to go ahead and click on that, and that opens our tuning software. It will automatically detect the tags in your trend, and it will select the PV and output. If for whatever reason it doesn't automatically detect the PV and output, you can hit the drop down and you can select what your PV and output are. And we're in the model builder. So the first thing we need to do is build that step response. And when you're building a step response, you need to ask yourself, how fast do we want to sample our data? Since this is a fast moving loop, it's a flow controller, I would say anywhere from 1 to 5 seconds is reasonable for sampling. If it's a slower moving controller, like a temperature loop, you may want to sample every 30 seconds, every minute. So I'm going to proceed with 5 seconds. And you always want to ensure you have that data in your historian as well. So in my historian, I do have that 5-second data. So I'm going to select a sample interval of 5 seconds. And then we need to pick our model type. So there's 2 model types. You can have integrating or first order. In this case, since we're tuning a flow controller, I'm going to pick first order. That's because those responses will settle, where integrating processes do not settle. So an example of an integrating process would be a tank level. As you add liquid to a tank, that tank will always ramp up unless you close your valve. So that's an example of an integrating process, a process that does not settle. So I'll pick first order since we have a flow controller. And now when I hit model, what this is going to do is it's going to use the raw data in my trend, and it's going to calculate the gain, lag, and delay. So I'll go ahead and hit model. And it analyzed the data in that trend, and it calculated a gain of 0.21 and a lag of 5 with a delay of 5. And then it goes out and draws that step response. So now we can visualize that step response right here. I'm going to save that model below. So now we have this saved model number 1 with our gain, lag, delay. We get some statistical parameters such as the model fit, what our R squared is, cross correlation, auto correlation. So overall, it's a pretty good fit. 81% is a good starting point. R squared of 96. What we can do is we can model different parts of the bump test, or we can even do a second bump test and model that again, just to ensure that our results are consistent. So I'll zoom in to the tail end of the bump test, hit model. I'll save that model. So now we have 2 models, both of a similar gain, which is good to see. We want to see consistent gain as we run multiple models. I'll create a third model here. Again, we see a consistent gain. So this tells me that the gain is most likely 0.21. A lag of 5 is pretty close to where we need to be. You can also change your model type as well. So we're using the basic UI, but if you uncheck this, you can move into the advanced UI. So you can actually adjust your modeling option. So the default model we use is non-least linear square, but if you're interested in using Box-Jenkins or ARX, you could pick those different model types. If you have some noise, you could pick Box-Jenkins and adjust your noise factors. Or if you want to stick with a linear model, you can pick ARX, hit model, save that model, and it's going to add that ARX method to our table now. So using ARX comes out with similar gain, 0.21. You can also unlock the UI. So if you manually want to put a custom gain in or a custom lag, what you do is you hit this little lock. It unlocks these boxes, and now you may want to test a gain of 0.25. You may have another method of calculating gain. You may have used Excel or some other software, and then we may want to try a lag of 10. So now if you plot that, it's going to draw out your gain of 0.25 and your lag of 10. If you move to the second page, the model prediction page, we could see how our model will fit the process. So the model in purple here and the process in blue, we could see the model follows the process nicely as the process was stepped down. And then as the process was stepped up, we're catching a similar magnitude of movement. It's very close. We get our statistical parameters, and then we even have a residual noise model. So in this case, we don't have much noise, but if you see this purple signal all over this chart, then we can go to Box-Jenkins and try to model out some of that noise. So this is a good example of a model with a well-fit model. So before we move on to Loop Tuner, where we get our PID, we want to ensure this fit is at least 60% or higher and try to get an R squared of 90%. If you can't get that, then you can go back to your raw data. You can try to do another bump test, try to ensure your process is stable when you're doing that bump test. And then when you do get that model fit of 60% or greater, then you can proceed the loop tuner to get your PID parameters for that DCS. So I'm going to move forward to the loop tuner. And the first thing you want to do in this loop tuner is pick your DCS type. So every DCS will have a different set of PID parameters. They all use different PID equations to calculate those parameters. So it's very important you pick the correct DCS type. So we support all the major DCSs. You can see there's ABB, Bailey, Delta V, Foxborough, Honeywell, Siemens, Valmet. And if there's a DCS type that is not included here, we can easily get that added. So just with any DCS documentation and manual, we can take their equations and get that added to the software. So we support all major DCS types. I'm going to proceed with Delta V for this example. And then the next thing you need to fill out is the OP span. So what span does this controller move? And a lot of this is already defined in your PID blocks in your DCS. So in my case, my OP span is 0 to 100. That's the range my valve can move from in the block. And then my PV span would be 20. So I'll update that there. And then the next question we need to ask is, how do we want to tune this? Do we want to tune this with proportional, with integral, with derivative, with combination of PI? Do we want to just do P? So in most cases, PI tuning is the most popular. So I'm going to select PI. So that's using proportional and integral with no derivative. And then this utilizes lambda tuning. So when I hit tune, it's going to use this lambda factor, this lag multiplier of 0.3, and it's going to simulate our plot with that gain we calculated in the model builder and the lag. So I'll go ahead and hit tune there. So now we can see our closed loop process variable response. I'm going to add our open loop response by checking this box here. You can even add your output if needed, if you want to see how your valve is working in the black. We can see we're kicking the valve pretty hard. It overshoots the valve, and then the valve needs to retrace and then settle. So that's pretty aggressive tuning there. So I'm going to back off on that tuning and slow it down. So the way to do that is you're going to want to increase your lambda. So lambda 0.3 is pretty fast for first order with time delay. So textbook theory for stable lambda is around 3. So as I increase my lambda, you're going to see this stable out. So I'll start increasing my lambda there. If you keep your eye on that simulation plot, you could see our response is going to stable out. And this would be appropriate tuning around 2 to 3. So that's going to be very stable. And then what I would do is I would try to speed this up as much as possible before causing any overshoot. So I'm going to keep an eye on my actuator, that black line, and the blue line, the closed loop response. So at a lambda 3, we're stable. Let's back off on that and try to speed it up, maybe around a lambda of 1.5. If we go any faster than 1.5, we're starting to see overshoot in our actuator. So there's no need to kick this actuator. I don't need to settle that quick. I don't want to introduce any aggressive tuning to my control loop. So I'm going to back off just a little bit. So I would tune this maybe around a lambda of 1.5, a lambda of 2. I think that's a safe spot to tune this loop here. That's the type of response we're looking for in lambda tuning. So now this tells us this loop should, in theory, settle, I would say, around a minute. It's going to hit 90%. And then at 100 seconds, you're going to be 100% closing the delta between your PV and set point. So now we have our new P&I. So our P for this tuning would be 0.3794, and our I, our reset, would be 11.6. What I always recommend doing is go to the custom tab right here. And what you can actually do is grab your current P&I in the DCS, and we can simulate what that looks like. So you may have a I of 0.1, maybe you have an integral of 20, sorry, a proportional 0.1 and an integral of 20. Maybe that's what's in your DCS. We can hit tune, and you have this type of response. So you can see this is a very sluggish response, right? It's going to take you 5 to 10 minutes to settle this type of response versus what the software is recommended is a settling time of 1 minute. So now you can see the before and after and have the confidence to make that loop tuning change. We can change the simulation settings as well. So you may be interested in a disturbance rejection simulation. So we can simulate that as well. We can simulate a disturbance and how we would settle from that disturbance. And finally, we have the reporting tab. This is where you can set up a directory anywhere on your computer or network. So I've created a generic directory to a tuning folder. And when I hit save, it's going to save all the work I've done here right into that directory. And anytime you come back to the tuning software, you can load that back into the software and have all your results the way they were preserved. So you can see it's created a custom folder called FC107 for hitting save, and it's going to timestamp each model. So here's my most recent model that I've created from February 3rd at 9:52 a.m. But if I'm curious of what I did last time in January, I can go back and load that right back into the software, and it's going to have my gain, my PI, what lambda we selected, all that work's going to be saved. So an easy way to document everything you do here and save all your work. And then finally, you can set up and generate reports. What this does is it's going to open up a Word document. You can make any modifications you need to that Word document, put any notes down to why you're tuning this loop, and then save that Word document. So we can see here, we used the model delta V. This is our calculated P&I. We have a P of 0.37, an I of 11. Always write down what you find your current tuning as in your DCS. That way, if you ever need to revert back to that tuning, you have that documented. So we found our current tuning of 0.1 and our integral of 20, and we're calculating our new tuning of 0.37 and 11. And then you can add some notes here. Please tune my loop. You can send it off as a work order, or you can just save this for documentation. That way, when the next engineer comes along, they're going to know exactly why you tuned this loop and where you left off. And then for integrating processes, there's some extra features involved because integrating is going to be used for tank levels. So let me select integrating. You're going to see you have the option to model your gain and lag with integrating, similar to what we did with first order, or you can rely on design data. Since we know the volumetric parameters of our tank, we can classify what the diameter is. We can classify the span of the tank. We can tell the system if the tank is reverse acting or direct acting. And we can change all the units here as well, right? So we may be in meters or feet. Maybe we want gallons per minute or feet cubed per hour. We can say if it's a direct level control or if it's not direct level control, and that is another method to calculating gain and lag. Or you could do both and see if they come out pretty similar. They should come out pretty similar if you do a bump test in a tank and you're calculating the design data for your vessel, your gain and lag should come out very similar. So you have two methods of doing that for integrating. And then the second part, let me just create an integrating model. So let me calculate. The second part, let's select this one, is for integrating loops, you'll be able to do a surge tank. So let me zoom in here, model. We're not going to find the best integrating response because we're using a flow controller, obviously, but I'm just trying to present the surge tank. So for tuning methods, when you tune an integrating loop, it's going to tune it for when that loop is critically damped because there's going to be no lambda tuning for integrating. It's tuning when it's critically damped and what that closed loop time constant is. But if you want to tune this as a surge tank, we can tell the system what the allowable level deviation is and what's the largest expected flow disturbance. And then it would give us the PID for a surge tank. So that is another feature as well, right? We could say we want our tank to deviate roughly 20%, and we could see a 5 to 10% flow disturbance to that tank, and it would keep your process very stable because you're allowing that disturbance to occur within your vessel because it's a surge tank. So that covers the tuning software. If there's any questions, please put them in the chat there and I'll go through and answer any questions you guys may have.